Hello everyone, and thank you for coming. I'm Moustafa Youssef from Egypt, Japan University of Science and Technology. And today I'm going to share with you our recent result on the Locationoid project, where we target an accurate and energy efficient localization for GSM phones in general and for the Android platform in particular. So as we all know, location-based services has been gaining momentum recently, and application ranges from finding the nearest pharmacy to are there any of my friends nearby now? Is there anyone interested in playing chess now? And so on. And the list of applications keep increasing every day. And there are commercial services that are being offered on a larger scale, like Google Latitude and Places, Facebook Places, and they keep coming every day, as I said. However, whenever we talk about localization for cell phone, we need to keep in mind the energy consumption of the localization technology we are using. Because of course, if your localization algorithms leads to depleting the battery very fast, no one will be willing to use it, because energy is a very scarce resource on mobile phones. Currently, the most commonly used and known technique for cell phone localization is GPS. However, GPS, as we all know, is an energy-hungry device. It consumes a lot of energy, as I will quantify later in my talk today. And it doesn't work in every place. So, for example, it doesn't work in indoors environments. It doesn't work in areas with tall buildings because it requires line of sight to the satellites. And at the same time, the recent applications like navigation, for example, in Google phones, Android-based phones, and Nokia phones, and other popular cell phones requires that you do your localization very frequently. So, for example, in order to track your car, you need to get the GPS location very frequently, and this can lead to killing the battery very fast on your cell phone. So, the problem we are trying to target is how to do localization on cell phones with high accuracy, but at the same time, you should be able to do it in an energy efficient manner so that you conserve the energy on your cell phone. So the Locationoid project, has different components. One of them, for example, is to perform a GSM-based localization using GSM network, not using GPS, so that you are not using the energy-hungry GPS device. Another component is to do power profiling for the different location components on the Android OS, so that we can quantify how much energy each component takes when it's running. And once we do this profiling, we propose an energy efficient technique for obtaining the cell phone location using the internal sensor. It is not using the GSM network nor using the GPS, but depending on the internal sensors, mainly the accelerometer and the compass. Finally, what we do in this project is that we propose a power management layer that runs on top of the location provider in the Android system that can combine all these components together to obtain, as I said, accurate and energy efficient localization system. So in the rest of my talk, I have two main components. The first one is CellSense, where we try to obtain an accurate location estimate in GSM network using probabilistic RSSI fingerprinting techniques. And in the second part, we propose JACK, which is a hybrid GPS accelerometer compass technique that uses the internal sensors to obtain the cell phone location with minimum energy. And finally, I will conclude my talk. So the first part of my talk is about CellSense, a probabilistic RSSI-based GSM localization system. And if we try to compare the GPS localization to GSM localization, we can see that GPS is an energy-hungry device, doesn't work in all areas. I said it doesn't work indoors, for example, and it is not available on all cell phones. It's only available on high-end cell phones. On the other hand, GSM-based localization systems consumes minimal energy, or if any, on top of the standard phone operation. Since your phone is already connected to the GSM network and it's performing the standard GSM protocol, if you do localization using the GSM signal, you are consuming minimal amount of power in addition to the standard GSM operation. So this is good. And it works everywhere GSM signal is available. So you are indoor, you can obtain a GSM signal. Your localization technique can work in indoor environments. And finally, GSM standard, according to Wikipedia, is available on 80 to 85% of the cell phones in the world. So again, you have a very large coverage in terms of devices. So it's attractive. So if we focus on GSM-based localization, the current techniques that are being deployed on cell phones, handset-based techniques, are mainly cell ID-based techniques or RSSI-based. By cell ID-based, what we mean is that if you have your cell phone and you can hear from a cell tower, the system estimates your location as the location of the cell tower you are associated with. This provides an efficient way of obtaining your location. However, it's a very coarse-grained accuracy, because on the average, your accuracy will be half of the coverage range of the cell tower. If you have more than one cell tower, like here we have 3 cell towers, your estimated location will be the center of mass of all the cell towers you can hear from. So as we said, this provides an efficient way of obtaining your location, but it's a very coarse-grained accuracy. Recently, there have been techniques that uses RSSI, the received signal strength, to estimate the cell phone location. However, since RSSI is a very complex function of distance, we cannot use a propagation model to estimate our location. Typically, what's being done is you use what we call an RF fingerprint. An RF fingerprint is basically you tabulate the characteristics of the signal strength at different locations in the area of interest. So for example, if I want to do cell phone localization in Mountain View, I go to different locations in Mountain View and collect signal strength information at different locations, and I store this information in what we call an RF fingerprint. It's a database of signal strength characteristics at different locations. During an online phase, the tracking phase, I am standing at an unknown location, and I am receiving a signal strength vector from different cell towers, and I'm trying to find the location in the fingerprint that I stored in offline phase that is closest to the received signal strength. You can imagine, of course, that using an RF fingerprint is a time-consuming process, because you have to go to different locations and stand there to collect the signal strengths. However, this is typically done in a process that's called war driving, where you ride your car and you have a cell phone with GPS that's connected to a computer, and you are collecting location information and signal strength information at the same time. And many of the current commercial systems like Street View and My Location from Google currently have cars that roams the streets. So in order, for example, to get the pictures of the streets in the Google Map application, and while you are doing this, you can piggyback your radio map construction in the same process. So it is not something that you have to do particularly for localization. You can do it for other applications too. So the word driving overhead is very minimal here too. So currently, there are, up to my knowledge, there are 2 main techniques for using RSSI localization in GSM networks. One is deterministic fingerprinting, and by this what I mean is that the red dots represent locations where you have the fingerprint. So at each of these locations, you stand and collect the signal strength characteristics. And here I assume you have only one cell tower, and the characteristics that is stored in the radio map in deterministic techniques is the average signal strength from this cell tower. So you stand at this location, you collect a number of samples, and you store in your radio maps the average signal strength you hear from this cell tower. The red dot represents an unknown location. You are currently standing at this yellow dot, and you want to know which of the red dots I am standing at currently. So in order to do that, deterministic fingerprinting techniques, what they do is they calculate the Euclidean distance between the unknown location, the signal strength at the unknown location, and the signal strength stored in the radio map. And they return the closest location in the radio map in terms of signal strength as the estimated location. So in this example, the closest location is -32 to -28, and it's returned as your estimated location. We believe that deterministic fingerprinting techniques provide coarse-grained accuracy, and that's why we propose probabilistic techniques that can help enhance the accuracy of localization, as I will talk in the next part of my talk. There have been also proposals using probabilistic techniques before. what is called Gaussian processes, and the idea here, their goal was to reduce the fingerprint construction overhead. So instead of collecting 1,000 samples, for example, you collect only 100, and then you try to interpolate these 100 samples to obtain more samples. So you are reducing the number of points you need to collect, and in order to do that, they assume a Gaussian process model and a propagation model to obtain the remaining of the samples. You can imagine in order to do these interpolations, your computational overhead will be very high, and actually, I believe that there is no actual reduction in terms of the overhead. Why? Because in order to collect 100 samples, you will need to do the word driving anyway. So if you do the word driving, it doesn't matter if you collect 100 samples or 1,000 samples because you already drove the streets. So it doesn't save much in terms of fingerprint size. So our approach is to use probabilistic fingerprinting, and hopefully we can obtain more accurate localization. And instead of storing in the radio maps, the red dots, the average signal strength, we need to store the entire signal strength histogram. So this gives you more information about the signal strength behavior, and using this extra information, you can obtain more accurate localization. However, the challenge here, in order to obtain a signal strength histogram, you need to stand at each location for a certain amount of time so that you can collect enough samples to construct your histogram. So by this, you are complicating the radio map construction process, because instead of driving continuously by your car, you will have to stop at each location. So this will increase your time significantly. So what we propose in CellSense is how can we reduce this overhead in terms of constructing the radio map. So I'll talk about the two phases, which is the offline phase, constructing the radio map, and then the tracking phase, estimating the location once you have your radio map in place. So in order to solve the overhead of the construction of the radio map, we use gridding approach. So your area of interest is divided into a grid where each cell represents a virtual location. So the idea here, again, the red dots represent the fingerprint location, where you collect these dots with continuous driving by your car. You don't have to stop at each point. You continuously drive, and based on your sampling rate, you will obtain these red dots. However, we construct the histogram not for each dot, but for each cell. So we use the points within each cell to construct the histogram of this cell, and then we use the center of mass of this cell as the radio map location. So we reduce the problem, instead of using each red dot to using the grid cell. Of course, we have a parameter here, which is the grid cell length, how large your grid size should be, and by this parameter, we can control the accuracy of the system and trade it off with the scalability of the system. Because the larger your cell size, the less your number of grid cells, and hence the better your scalability, but your accuracy will decrease. And we'll quantify this later in the evaluation section. So this is the offline phase. What we do is we divide the area into grid cell and construct a histogram for each cell. During the tracking phase, you are standing at unknown location L, and you want to find, you are receiving a signal strength vector of Q dimension, where Q is the number of cell towers you can hear. In the GSM standards, you can hear up to 7 cell towers. So each component represents the signal strength from one sample from a cell tower. And what we want to find is the location L in the radio maps that maximizes the probability of this L giving the received signal strength vector S. Using Bayesian inversion, you can find that probability of L given S equals the probability of, not equal, the locations that maximizes the probability of L given S is the same locations that maximizes the probability of S given L. And I remind you, the probability of S given L is what we stored in the radio map. So this information on the right-hand side can be obtained from the constructed radio map. Assuming the cell towers are independent, you can obtain this by multiplying the individual components. And in order to enhance our the accuracy of our techniques better, what we do is that we use more than one sample. So instead of using just one sample for estimation, we use n samples at one time for estimation. You have more information, so you should expect to get a better accuracy. And in this case, you multiply the samples and the cell towers. We have also a post-processing step where we average, instead of returning the most probable location, we return the average of the top k most probable locations. And we see also that this enhances our location estimation process. So how well did we perform? In order to test our system, we experimented with 2 different test beds. One in the smart village in Cairo, which is a typical rural area, and another in Alexandria, which is a typical urban area. We have 2 data sets, one for testing and an independent one for training for the 2 different test beds. And of course, in the rural area, you can notice that the density of cell towers is less than the density of cell towers in the urban area. This figure shows the median error as we change the grid cell size. So as expected, as you increase the grid cell size, what happens is that your localization accuracy decreases since your size of the grid size increases. However, if you look at 400 meter grid size, you can see the accuracy is comparable to very low grid sizes. So this is good news that you can have relatively large cell sizes, but at the same time, you can obtain good accuracy. In terms of the number of samples you use concurrently to estimate your location, you can see as we increase the number of samples we use in location estimates, your accuracy trend is enhancing. But at the same time, you require to wait more samples in order to get these n samples. So your latency will increase. So you'll have a trade-off between latency and the accuracy of location estimation. This is the last parameter, which is how many locations you average as a post-processing step. So instead of returning the most probable location, you return the k most probable, the average of the most k probable locations. And again, as you see, as you increase the value of k, your accuracy median error decreases and your accuracy is enhanced. Comparing our technique to other techniques, we compare our technique CellSense, which is the red curve, with the deterministic fingerprinting techniques, the blue curve, and the Gaussian processes, the green curve, and with Google My Location technique, which is the purple curve. For Google, what we do is that we send the query, the cell tower, using the Google API to the servers, and we obtain the location estimates. The other 2 techniques we implemented as we implemented our system. We can see from the figures, this is the CDF of distance error, which gives you the probability of that your location will be less than a certain error. So you can see the median error at 0.5 for our technique is better than the other techniques with at least 23.8%. This was in the rural areas. For the urban areas, we have even better accuracy. We can achieve up to 86.4% better than any of the other techniques. This table summarizes the results in number. I'm not sure if it's clear. In terms of running time, we are slightly more than the deterministic fingerprinting techniques. The probabilistic fingerprinting techniques gives about 76 milliseconds per location estimate, and our technique takes about 90 milliseconds per location estimates. Google My Location, of course, since it's cell ID based, it doesn't do a lot of processing, so it's about 12 milliseconds to obtain your location estimates. So as we said, you have a trade-off between time and accuracy. So in conclusion, CellSense is a probabilistic fingerprint-based GSM localization technique that uses grading to reduce the fingerprint construction overhead and to scale the system. And its accuracy is better than any of the current techniques for GSM localization by at least 23.8% in rural areas and 86.4% in urban areas. I now switch gears to another localization system, which we developed within the context of this project, which is JAC, a hybrid GPS accelerometer compass localization scheme. This technique doesn't use GSM for localization, but instead uses the accelerometer and the compass available in smartphones in order to do localization combined with the GPS. So the motivation for this work is that many of today's smartphones contains accelerometer and the compass, and it's mainly used for screen auto-rotation. So if you rotate your phone, this rotation action is detected by the accelerometer. So the accelerometer is continuously running. It's used for gaming, control, and for many other applications like flip to silent, you flip your phone in order to silence it. And whenever people talk about localization techniques, they usually focus on the accuracy of the localization technique, and they ignore the dimension of energy consumption. However, if you think about it, at some applications, I don't need very high accuracy of localization. So for example, for me, if I need just to know that I am in mountain view, I'd be happy with a 1 kilometer accuracy. I don't need meter accuracy. 1 kilometer would be very fine for me. So can I leverage this coarse-grained accuracy to reduce the energy consumption of my localization technique? And this is what we are trying to target here. We are trying to study this trade-off and give control to the application developer so that he can choose whether he needs accurate localization or an energy-efficient localization. The Jack approach, simply the overall idea is that it obtains an initial position estimate using GPS, and then it turns off the GPS and switches to the accelerometer and the compass to estimate the location. And from time to time, it synchronizes back with the GPS because of the accumulation of error. So instead of using the GPS continuously, you are duty cycling it with very, very low duty cycle to enhance your energy consumption. So in this part of the talk, I'll start by talking about the Android power profiling for the different location components in the Android phone. And then I talk about our proposed hybrid technique. And finally, I'll touch on the power-aware location power management layer in the location platform. And finally, I will conclude. So in order to profile the power consumption of the different location components, we did it on an Android Dream G1 phone. And we used a monsoon power monitoring device. And the way it works is that you replace the battery of your cell phone with a battery that comes with the device, and you connect it to the device, and you have an application running on your computer that tells you the current drained from the battery, so that you can, when you are running different components, you can know which component is using which amount of current. And since voltage is constant, you can use the current as an indication of the power consumption. The battery that is used provide 1150 milliampere hour. This is the capacity of the battery. For the GPS, we can see this is the typical curve you get from your power monitoring device. When you turn it on, it almost consumes an average of about 140 milliampere hour. Sorry, 100 milliampere. For the accelerometer and the compass, the chip that comes on the HTC Dream phone combine the accelerometer and the compass on the same chip. This means that if you are querying the compass or you are querying the accelerometer, both of them are running and you are almost consuming the same amount of power. And you have a 3D accelerometer from this chip. The Android API provides 4 different data rates for querying the Android accelerometer. And this is a typical curve you can get from when the accelerometer is running in the user interface mode. You can see it consumes about 40 or 45 average current during its operation. We'll quantify this more in numbers later. So these are the different 4 modes of operation. You have the normal data mode where you can have 4 samples per second, up to the fastest mode where you can have up to 50 samples per second. And the power consumption is not linear in the number of samples you collect. And our hypothesis for that is that you have 2 modes of operation, slow and fast. And that's why it is not linear. However, we didn't have access to the data sheet of the accelerometer and the compass chip to confirm our hypothesis for that. Comparing the different techniques, you can see the GPS consumes about 140 milliampere when it's running. Compared to the normal mode of operation of the accelerometer, it's more than an order of magnitude more power consumption, which gives you an idea that if you run the GPS, for example, it consumes 11.73 of the battery in 1 hour, which means that your battery you can run for 8 or 9 hours. If you use the accelerometer in the normal mode, your battery would run to 100 hours. So it's significant saving in energy if you can turn off the GPS and depend on the accelerometer for your location estimates. As another advantage, I'm telling you that the accelerometer is already running all the time in the background so that the operating system can detect the auto orientation of the phone, that you change the orientation of the phone. So again, if you base your estimate on the accelerometer in the normal mode, you are not consuming any more energy than the standard phone operation. So you are getting it for zero energy consumption in addition to the standard phone operation. So this is an extra advantage. So we'll talk about how we leverage this in our estimation. As we mentioned, the basic, this is a state machine of the very simple state machine of the jack operation. You have a synchronization state and the estimation state. In the synchronization state, you obtain a GPS location estimate, and you also calculate the current speed from the GPS and calculate the offset between the accelerometer speed estimated from the accelerometer and speed estimated from GPS for correction. I'll show it to you in the demo. Once you obtain this information, you obtain a fix, or after a certain amount of time, you switch to the estimation process where you switch off the GPS and base all your estimates on the accelerometer and compass only. And from the accelerometer and the compass, you obtain the displacement and direction, and you combine them to obtain your new estimates. And periodically, from time to time, you switch back to synchronization state to compensate for the accumulated error, and this repeats forever until your localization is done. In order to obtain the position estimate, we use the standard Newton laws to obtain the position estimates for the accelerometer and the compass. I will not go into the details. The only thing I need to highlight here is that we need to take the curvature of Earth into account. Since the Earth is like a sphere, you cannot use Euclidean distance in order to calculate your location. Instead, we use the Vicenti's formula, which is an accurate 2 millimeter accuracy on the Earth's ellipsoid in order to obtain the location estimates. Okay, in order to evaluate our system, we had two different test beds, one in highways and the other inside the cities. And we studied the effect of changing the synchronization period on accuracy. And we compare our system with InLoc. InLoc is similar to our system with the exception that it doesn't use accelerometer or compass. So the way it works is that it obtains a GPS fix. It estimates the current speed and the direction, and that it assumes that this speed and direction will be fixed until the next synchronization point. It doesn't use accelerometer and compass in between. So we compare our system with this very simple technique using linear prediction. In order to evaluate our system, we had a debugging tool based on Google Maps where we draw the GPS traces and the estimated traces, and I can show you an actual demo from it. So what we are seeing here is the debugging tool. It gives you information like the total trip distance on the top, then the trip duration, your average speed, your error at the final point of the trace, your root mean square error, and your maximum error. And you can control the synchronization frequency in second. Currently it's set, as you can see here, the current value is 10 seconds. So this means that every 10 seconds you turn on your GPS to synchronize with it, and you can change it up to 102 minutes so that to see the effects. And down here you can see the trace. This is a highway in Alexandria city. The green ticks represents the GPS trace, which is taken as the ground truth. And these yellow and red ticks represent our estimated location. The yellow dots represent the synchronization period, the period you turn on the GPS, and then you, after the yellow dots ticks finish, your GPS is completely turned on, and you are only using the accelerometer and the compass for estimating the location. And it's 10 seconds, that's why it's short. We'll change it now to see the effect. You can see, for example, if I am synchronizing every 10 seconds, my estimate is very accurate to some extent. My root mean square error is 6 meters. If I increase it, for example, to 60 synchronization every minute, instead of every second, I synchronize it to every minute, you can see the error accumulation here. So again, you have the same, you turn GPS for the same period, and the red period is where the GPS is completely turned off. You have a lower duty cycle, so your energy consumption is much less, but at the same time, you are not synchronizing with the GPS more frequently, so you have more accumulation of error. I remind you here, we are not using any heuristics on top of the localization system. So I am not using the street map to match the estimated location to, I can snap it to the street. I'm not doing this here. We can, of course, enhance this, but we are not doing this here. Of course, you can click on any point, and they give you more information. If you click on the point, it tells you when it was collected from the start of the trace, GPS speed, estimated speed. You can see that the GPS speed was 16.5, and our estimated speed from the accelerometer was 16.6, very close. It gives you the X and Y acceleration, gives you the GPS altitude and the accuracy of the GPS. We have other figures too. This is the same point I clicked on the different figure. The blue curve gives you the estimated GPS speed, and the red curve gives you the estimated speed using the accelerometer and the compass, or jack in general. And you can see there is a drift in the middle, and that's the cause of the drift from the actual position. And at this point, there was a synchronization with the GPS. That's why the accuracy was snapped again to the estimated location. We have our this is for the accelerometer. For the compass, the blue curve is the direction estimated from the GPS. The red curve is the direction estimated from the compass. And you can see there is an offset between the two. In order to correct for this offset, what we do is that during the synchronization period, we calculate this offset, and then we remove it from the estimated direction. So during this period, we estimate this offset, and we subtract the offset from this curve, which gives you the orange curve on top of the blue curve. We have other figures like the accelerometer reading and the difference from the true acceleration and the estimated acceleration. You can see it's within plus or negative 0.2 meters squared per second. Let's go back and see numbers. This is the debugging tool where it gives us the numbers, accuracy, and so on. In terms of power consumption, what we see here is comparison between the different techniques for different synchronization periods on the x-axis in seconds, and the y-axis gives us the milliampere hour consumption of different techniques. You can see that GPS, if you leave it on all the time, it consumes, as we said, about 140 milliampere per hour. For our technique, comparing our technique to the in-lock is slightly better than our technique in terms of energy, and the reason for that, as we said, in-lock doesn't use the accelerometer and the compass, and our technique uses the accelerometer. So the difference between the blue curve and the green curve is the power consumption of the accelerometer and the compass. However, as I mentioned, since the accelerometer is running all the time in the background to detect the change in the orientation of the phone, we are not using any extra power consumption on top of the standard operation. If you take this into account and remove it, we find that our technique consumes the same amount of energy as the in-lock technique. So we are consuming the same amount of energy, and you can see that the saving in power consumption is exponential compared to the GPS. As you increase your synchronization time, your saving in power consumption decreases exponentially. So this is significant saving. In terms of accuracy, this shows the accuracy for highways. Let's focus first on the green and the blue curves. The green curve is our technique root mean square error, and the blue curve is the in-lock linear predictor root mean square error. You can see that for short synchronization period up to 50 seconds, there is no difference between the two techniques. However, as you increase your synchronization period beyond that, in-lock is actually gives better accuracy than our technique. And the reason for that is that here we are on the highways where you are usually moving in a straight line. So the assumption if in-lock is accurate, we are using the accelerometer and the compass, but we are not synchronizing frequently enough. So we have accumulation of error that decreases our accuracy. So as we see, I said, in small synchronization period, we have the same accuracy, but if you want to move to higher synchronization period, in-lock will be better for you if you are using the highway. The main advantage of our technique appears in intra-city driving. So here we are driving inside the city, and again, the green curve is our technique, and the blue curve is in-lock technique. And you can see that we are significantly better than in terms of accuracy in-lock, even for small synchronization period. And the reason here is that the in-lock assumption of moving in a straight line is no longer valid, because within city you are changing directions, making turns and so on, and also you are changing acceleration. In-lock assumes that the acceleration would be fixed until the next synchronization point, which is not true when you are moving inside the city. You are accelerating and deaccelerating because of the traffic. The nice thing here is that the red curve gives you the power consumption. So what you can see that we are saving exponentially in terms of energy, but we are losing linear in terms of accuracy. So you can benefit significantly in terms of energy consumption with very little loss in accuracy using our technique. So I'll touch briefly on the power-aware management layer in the location platform. Currently, in order to obtain your location estimate, what you have to do is construct a location listener, register it with the location provider, and you specify whether you need to use GPS or network-based provider. And when you are done, you unregister your listener, and that's it. However, the developer doesn't have control over the accuracy or energy he is requiring. All he can say is that I need my location update, for example, every 10 seconds or whatever. He cannot say that I need my accuracy to within 1 kilometer or 10 meters or whatever. He give it in terms of power or energy budget. He cannot say that I need an accurate location so that my battery can last for 10 hours or for 1 day, for example. The developer doesn't have control over this. It would be ideal if we can extend the location provider of the Android operating system so that we can give this API to the developer so that he can have the old API and the new API that gives him control or her over the energy accuracy trade-off that we presented in the previous technique. So this is what we are proposing, to have a power management layer where the application requests the location accuracy and the energy or synchronization frequency, and the power management layer will determine the best location provider to use and how long it should use and how frequently it should report the accuracy. To give you an idea about the saving, this figure shows the accuracy of the GPS chip when the GPS is turned for 60 seconds, and this is done periodically. You can see that you start with very coarse-grained accuracy when you have a cold start, and your accuracy drops exponentially, and then it saturates at the end. So at the end, you are consuming, you are almost having the same accuracy, but you are consuming power with no enhancement in accuracy. It would be better if I can stop, I say I don't want any more accuracies, this accuracy is good enough for me, and then switch off the GPS chip to enhance your energy efficiency. This is the same curve, but running it for 10 seconds, and as I said, if I am good with 250 accuracy, so why not turn off the chip to save energy? So in summary, what we provided in the second part of my talk is power profiling for the GPS and accelerometer and the compass on the HTC Dream Android Power mobile phones. We showed that GPS consumes an order of magnitude energy more than the accelerometer and the compass, and we proposed a hybrid GPS accelerometer compass-based scheme that uses the accelerometer very infrequently in order to do synchronization, and then depends on the accelerometer and the compass to reduce the energy consumption. We showed that our technique can give exponential saving in energy with a linear loss in accuracy, which is very promising. And our scheme doesn't lead to significant improvement in highways when you are having over in lock, when you are having long synchronization period. However, it has significant improvement inside cities where you have large number of turns and accelerations and deaccelerations. Currently, we are working on performing complete power profiling for the Android platform of the different components so that you are taking the operating system overhead into account also in the power management layer. And we are also thinking of integrating the power profiling results into the Android emulator so that when developers are working on the emulator of the Android phones, they can have a sense of how long the battery will last when you are using this component or this technique on your phone. We are also experimenting with using Kalman filters and other statistical technique to further enhance the accuracy, and also experimenting with dynamically adapting the synchronization period. And instead of having a fixed synchronization period, how can we adaptively change it based on the accuracy so that we can further enhance the energy consumption. I would like to acknowledge Google for their support for this research, and this concludes my talk. Questions? Can you raise your? Yes. So in order to do this experiment, we assumed that the orientation, the phone is fixed, can maybe on the dashboard of the car or in your bicycle. So the question was, can you talk more about how can you handle the different orientations? The Android phones come with an orientation sensor at the same time, so you can experiment with taking this reading in order to detect the orientation of the phone and then reorient it to the standard coordinates and use it. Once it's oriented, you can use the same technique without any modifications. However, our initial results on that shows that you have very large amount of noise. It is not that accurate. But again, if you assume that mostly when you are driving, you will not be carrying the phone in your hand. It will be fixed with some orientation on the dashboard. So for example, you can do an initial calibration when you start your system and then use it from there. Other questions?
Did you examine switching between a lock and your system based on the kind of driving person's doing?
Very interesting question. The question is, we said that in-lock is better in highways than our technique, and then we are better in intra-city. So did you thought about switching between the two techniques based on the driving better? Yes, and actually I didn't include it in the current work. One way, of course, is combining both techniques. So for example, you can detect from the movement better from the accelerometer that the user is driving with a constant speed, or he's not making a large number of turns, and based on this you can say I am on the highway. So in this case, I can switch completely to in-lock and disable the accelerometer and the compass. It will give me better accuracy and it will save me more energy. So this is a very good idea. Yeah. Other questions? Ahmed. I have 1 or 2 towers. The question here is that in the first technique where we are doing RSSI-based GSM localization, if you have an area with a sparse radio map, sparse cell tower density, you have say 2 cell towers, and you will have many locations with similar fingerprint, meaning the signal strength at this location would be the same. So how would you do? Will you select one of them randomly, or you select the topmost? The parameter I showed, which is K, which is a post-processing step, what it does is that it returns to you the average of the topmost K locations. So in this case, if you have 2 locations with similar fingerprint, what it will does, it will give you to use the center of mass of these similar locations. And it will be weighted by the probability. So when you are taking the average, it's a weighted average using the probability. So the location with the highest probability will have more weight than the location with a low probability. So in this case, you are taking a weighted average, it's center of mass. Actually, it's the center of mass of all location, taking weight as the probability of the location. Of course, your localization accuracy will not be as good as when you have 7 towers. But in this case, this is the best you can do. Okay, actually, I was talking with another group in the morning about same idea, which is how can you do localization with low-end phones where you get information only actually from one cell tower, not two. So if you have a low-end phone, usually it will give you just the information from the associated cell tower. So if you are doing this, how can I enhance the accuracy based on this? And one technique is what you are talking about, is taking the history information into account so that I can get a better estimate. So I'm not just taking this sample, I'm taking the history of sample with me to further enhance the accuracy. Right. Actually, independence assumption is usually taken for mathematical feasibility and tractability. Actually, we haven't experimented with taking correlation into account. Actually, in a previous work in Wi-Fi based localization, we had a work for taking correlation between samples from the same access point. Actually, you can go with the assumptions that samples from different cell towers are independent. But when we talked about using n samples at the same time, we assume that samples from the same tower are independent. But actually, they are very highly correlated. So you modeled this before using autoregression, and we obtained better results when we take correlation into account. But it will take you more processing overhead in order to remove this correlation. So it's can also and do a correlation like what happens in the assisted GPS, for example. Yeah, that's a valid point too. Very good question. Sure. Right, that's a good question. The question is, did you try to use different phones in your experiment, or you just used one phone? Because when you use different phones, each one has a different receiver sensitivity, so the radio map constructed by one will be different from the radio map constructed from the other. Actually, what we did is that all the phones we used were G1 phones, but we used different G1 phones. So at least from the same model, we tried different phones, and all of them, of course, gave similar results. We tried with Nexus 1 phones, but we didn't have concrete results, figured draft. We just had it in a demo that we can walk and give us similar accuracy. What we did also is we tried different service providers. So not just one service provider. We tried with Egypt has 3 major providers, and we tried with the 3 of them, and they give us comparable results, of course, depending on the cell tower density. What we also planning to do is to do automatic mapping between different phones. So even if there is a difference between phones in terms of the receiver sensitivity and antenna pattern and so on, can we have an automatic way of taking a radio map constructed by one phone and map it automatically to another phone? This is something that we are looking into now too. That's a very good question. Arunj. In which technique? The first technique, of course. In Egypt, we didn't have any significant tall buildings that can affect the reception. As I said, we are taking GPS as ground truth. So for this, we are assuming it has 0 error. So no, the answer, we didn't try any canyons or so on. If you have a data that we can use for evaluation, it would be great to look into it. Thanks. You had another question? Mm-hmm. The way we do it is that on the streets. Yes. So have you tried actually in the evaluation phase? Have you tried actually walking the building and actually hear the location served by a fingerprint versus your actual location? Again, not formally, so we don't have figures for this, but we do it on the demo. So you'll be inside the building that will give you a location better than the we had actually a demo. Of course, it is not calibrated here, but where you can show, we have a demo where you can show the 4 techniques I'm comparing with, and you can see the estimated location using all the techniques, and it could have the same accuracy. But we didn't have an exact number that your accuracy degrades by this amount when you are doing this. Sure.
Another comment I have is about the power management you mentioned at the end. So one of the things you mentioned is you feel like you want to empower such a capability to the user so that every application can actually decide which particular power scheme that the location provider might endorse. But in reality, there are so many different applications running on the same phone. So it looks like you really have like a management problem where these different give you conflicting goals. There are certain applications that just don't care about power. There are certain applications that don't care about power. How do you kind of balance that? You want to enable per application basically?
Good question. The question is, when I talked about the power management layer on top of the location provider, we said that I'll give the application developer an API to specify his accuracy and energy consumption requirements. So the question was, what if you have conflicting applications, each one of them requesting a different criteria that conflict at the power management layer? So this is a very good question, just from the top of my head. In the worst case, you will be working with the least of them. So in this case, you are not doing any worse than the current API. But if you can do better, you will do better. Something similar that you introduced in the latest API is that, if I remember, scheduling events instead of waking up randomly, you combine applications that wake up at the same period of time and make them all wake at the same time. So if everyone say I need to wake every 10 seconds and you are spaced apart every second, actually you will be waking up every second, not every 10 seconds. So what you can do is that you align them together so that you can obtain same thing. So maybe something along these lines can be used in the location provider too. But actually it's an interesting problem that needs more thoughts about it. Yeah. Any questions?
How long does it take these PS line part to fix back on?
It depends on many factors, including are you indoors, outdoors, have a clear line of sight to satellites or not, is it a cold start or warm start, and so on. So there are a lot of factors in our technique. If you remember the state machine, we're saying obtain a fix or timeout. So this timeout is used that if your fix takes a lot of time, then you will time out and move to the estimation speed so that you don't consume a lot of energy waiting for a GPS fix. And hopefully when you come later to the synchronization state, you will start from, not from the beginning, from some point, so that you will enhance the, take shorter time in order to obtain the next fix.
So is this time part of the synchronization period?
It's fixed, as I said, from the demo, as you saw, the synchronization period was fixed. We fixed it at some time. When you increase it, it's the start. The time I was showing in the x-axis is the start of synchronization period. And then the time you stay in synchronization period is fixed regardless of the synchronization period. Okay.
And do you have a similar graph for the city driving?
For what?
Intra-city driving?
You need intra-city driving.
Yeah, the error definitely graph for that.
This one?
No, the Google Maps thing where it showed the error.
Oh, I don't think I have the data set. All of them are highway. You talk about this?
Yeah.
I think all the data set I have here is for the highways. Sorry for that.
Does the
Because
good job make a turn, or does it just not?
does what?
Does it good job estimation mean make a sharp turn?
Actually, the turn, we take it more from the compass. So when you make a turn, the compass will give you a better estimate of the direction. So we just take the accelerometer to estimate the displacement, how much you moved along this direction. That's why we combine both. Actually, in the slides, here this is from intra-city driving, but I don't have the data with me. So this is within city, but it's static. It is not, I cannot change the parameters. Okay. Inside what?
inside a car.
A car.
And some of the, because the car itself has very strong magnetic field. So it seems to me like it work when it comes back and it works inside the car.
Because of the magnetic field.
Yeah, because the car itself has
So the question is, if you use the compass inside the car, there is a magnetic field that may affect the accuracy of the compass. Right, and actually we are showing it here. We do have it, and in order to reduce it, we do some averaging and filtering on the accelerometer compass reading. And that's why maybe this is one of the reasons, this figure I was talking about, this is the reading from the compass, from an actual experiment inside a car. And the blue curve is the estimated direction from the GPS. The red curve is the raw data you get from the compass, reading from the phone. And the orange curve is the corrected figure taking the offset into account, the initial offset into account. So if you just use it, actually the red curve is an averaging of the raw data. And then on top of this, we do more processing to obtain the orange curve. So yes, it's noisy, but we try to reduce the noise by some processing on top of that. Okay. Any more questions? Okay. Thank you very much for your time.